going to talk about is some of the important chemicals that are involved with life itself. Some of the important molecules, some of the atoms involved in life, how those atoms and molecules are put together to form things like compounds, um, how scientists look at those atoms and how we define kind of what they are, how we figure out what makes up an atom, what makes up compounds, what makes up molecules, some of the really important different types of chemicals that are involved in life, some of the different major classifications that are found in all different living organisms. And a couple of other things involved with some concepts like that. What makes up those things, those little molecules that are important for life, and some other things like that. So let's go ahead and get started with that. So, the first thing that you guys need to understand is the concept of matter and atoms. So, if you put your hand on a table, you're going to feel it. And what you're feeling is stuff. It's matter. It's physical being, physical existence. So, physical existence in its simplest form is made up of something called matter. So, matter, you guys are probably familiar with the states of matter, liquid, solid, gas, plasma. You guys are probably familiar with those concepts. So those physical states matter. It's kind of the idea of stuff, kind of things. It gives physical things their thingness, if you like. Gives something their being. So if you stick a little bit of matter together, you get space. And if you stick a little bit of that matter together, you get something called an atom. And if you stick a couple of atoms that are the same, we'll talk about what an atom is in just a second, you get something called an element. So an element is the purest form of something out there. So it's something that you can't break down any farther than its pure self by chemical processes, just by like adding acids and things like that, that you have to have a laboratory or like unnatural means to do so. Things that just aren't going to happen by themselves in nature. So um, try if you take a thing of gold, like a little gold nugget of pure 24 karat gold, pure atoms of gold. All the atoms inside of it are identical. They all are the exact same gold. That is an element. It's the exact same. You cannot get anything else in there that is not gold. It is all gold. Something that's like 18 karat gold, however, has gold and maybe silver, nickel, little other elements, different atoms added into it. So it's not a pure element. You can get different things out of it. You can get other elements and other atoms out of it. So it's not just the same. An element of things like sodium, all the atoms in there, all of the things are going to be identical. They're all going to be sodium atoms. If you break it apart, they're all going to be identical. They're not going to be anything separate. It's all going to be the same. So that's what an element is. So all the elements that we know about as humans are put together and classified on something called the periodic table. Now, you guys have probably seen the periodic table. It is a very, very, very common thing in pretty much every science lab across the planet. Now, how is this thing put together? So these things, this is the top half of the periodic table. These are the really important elements that are known for life. Life requires pretty much all of these things. The rest of the elements down here are not so much important for life. They're more chemistry based, not so much for biology based. So we're kind of going to just stick up here in the more biology section of the periodic table. So you guys can see down here, bulk elements, things that we need in large amounts of for life on Earth to go on. We need large amounts of hydrogen, carbon, nitrogen, oxygen, things like that for our life to exist. And then you have trace elements like chromium, magnesium, iron, things like that, zinc. That are required for life on Earth to go on, just in small amounts. So you need large amounts of the bulk elements, and then tiny traces amounts for your cells and all of the other life on Earth to be happy. Large amounts of these in your diet, large amounts of these for us to use, and then little amounts of these in your diet for your cells and things to use. So we will talk about what the periodic table means, how you read this, what all this stuff up here means, what all these numbers and symbols mean individually here in just a second. So, um, so the first thing that we're going to talk about is the element itself. You will see down here a lot of these periodic tables. This is an abbreviated periodic table. It doesn't have all the stuff on it. But then when you zoom in, you'll find full periodic tables that have all the information on it. So you'll find the very first thing here, which is the element's name. A lot of the time you'll find the symbol, which is the abbreviated version of this. So O for oxygen, N for nitrogen. A lot of them make sense. They're just the first letter or the first two letters. Some of them are, say, gold, Ag and Au, things for silica, for salt, silver, and gold, come from their Greek names or their Roman names, Latin names. So AU and AG is what the first two letters, the first couple letters or whatever it was in the previous language before it was translated to English. So these symbols represent what the element itself is. So sometimes you will see the full name printed on a periodic table, and sometimes you'll just see the symbol. So that's what the element name, that's what these things mean. So we'll go over what the rest of them mean here in just a second. The atomic number and the atomic mass. So these things are very important. These things are put together 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth, all the way up. Now, what these numbers represent, and why the atoms and elements and things are put together in the order that they are, is dependent on the atomic number. Now, what the atomic number is it's the representation of the amount of protons that are found inside of an atom. Now, let's talk about what an atom is. So an atom is the smallest piece of an element. So you could pull apart an element. You have a big chunk of gold. You pull out one atom of that element, one atom of gold. It's going to be gold. If you break that apart, it's not going to be gold anymore. It's going to be something else. Whatever that smallest amount that you can identify as gold is going to be considered an atom of gold. One atom is the smallest, purest thing that retains all the characteristics of gold that we can identify as gold. If you break it apart, or if it falls apart or whatever, it's no longer going to be that element anymore. And it's no longer going to be the same. It loses the characteristics of that atom, of the previous element anymore. So anyway, an atom is made up of three different things. You have protons, neutrons, and electrons. Now, these things are called subatomic particles, and the number of protons and neutrons and electrons are going to be unique to each different type of element. So all the atoms that make up the element of gold will all have the same number of protons and neutrons for the most part. All the atoms that make up sodium, all the atoms that make up hydrogen, they will all have the different, but this from all the other elements, but the same within all the element itself. So all the elements, the atoms of nitrogen, will have the same amount of protons, the same amount of neutrons, but they will none of the other elements will have the same amount as nitrogen. They will all have different numbers. So the same within the same element, but different than all the rest of them. So anyway, protons, neutrons, and electrons. So protons and neutrons are grouped together in the center of an atom. You guys have probably seen this picture before if you watch The Big Bang Theory, the little intro screen, or maybe Jimmy Neutron, an old cartoon, things like that. You probably are familiar with this representation of an atom. So in the middle, you will find something called the nucleus, and this is a cluster of protons and neutrons. They're grouped together in the middle with the electrons flying around the outside of them very, very, very quickly in something called an orbital. So you guys, they move very, very, very quickly. We don't know where they are at in space. You can just see kind of the cloud that they occupy. They move so fast you can't really see where they're at. You can just see the space where they occupy, kind of thing. It's like a big fuzzy cloud. They move so quick you can't really see them. So anyway, protons, electrons, and neutrons all have charges on them, or the lack of charges, I should say. So protons themselves, P proton, positive. They have a positive type charge to them, a positive charge, just like a magnet. Electrons, on the other hand, have a negative type charge. So protons and electrons, protons are found in the nucleus, electrons on the outside of the atom, flying around the nucleus. Protons and electrons, since they both have positive, they both have protons have positive, electrons have negative. These two numbers tend to be equal. The number of protons, the number of electrons in an atom tend to be equal. If you have 5 protons, you tend to have 5 electrons. 5 positive charges, 5 negative charges, and they cancel each other out. Atoms tend to not have charges. The numbers of electrons and protons tend to be equal. They tend to not have a charge on the atom. Sometimes they will take those on. We'll talk about those later on. But most often they don't have a charge. The number of protons, numbers of positive charges, equals the number of electrons, the negative charge. Now, neutrons, the other option, the other subatomic particle found in the nucleus, has no charge here. It has no positive, it has no negative, so it does not influence the charge of the atom whatsoever. So anyway, onwards to the atomic number. The atomic number represents the number of protons that are going to be found inside of the nucleus. So if we take a step back, you guys know protons represent positive numbers. So positive protons, that's the number of protons that are found in the nucleus of oxygen. If you are an atom of oxygen, you will always have 8 protons inside your nucleus. You could have 14 billion neutrons and 18 trillion electrons. As long as you have 8 protons, you will be oxygen. That is kind of the definitive characteristic of oxygen. It's kind of like chromosome numbers in organisms. We have 42 chromosomes, or 46 chromosomes, or 23 pairs. And that is what makes us a human organism. Anything different than that, you are not a human. The same thing works with atoms. You have 7 protons, you are nitrogen, 6 protons, you are carbon. Anything other than 6, you're something other. And you can see hydrogen has 1, so on and so forth. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. You guys get the idea. The number of protons you have puts you in order from the least one all the way up. As you go this way and down, you get more protons. And that's how the periodic table is organized. So the first number that you see is the atomic number. That number tells you the number of protons. Well, since we also know that the number of protons is equal to the number of electrons, because atoms have a negative charge, or a neutral charge, excuse me. Protons are positively charged, electrons are negatively charged. They balance each other out to give a neutral charge. So if oxygen here has 8 protons, which we know from the atomic number, it also more than likely is going to have 8 electrons. So that's pretty much what we're always going to go with. 8 protons equals 8 electrons. So we know that because positive equals negative, they cancel each other out. 8 protons, you're going to have 8 electrons to cancel the positives out, and that's what you get. So the atomic number not only tells you the number of protons, it also tells you the number of electrons that are found inside of that element. So nitrogen here has 7 protons, 7 positive charges. It's also going to have 7 electrons, 7 negative charges. So you guys will see down here the mass number. Down here, the atomic mass, 15.9994 for oxygen. Sometimes they're rounded up to 16. Nitrogen, 14. Carbon, 12. You guys get the idea down here. They're usually either rounded up sometimes or left like this, depending on the periodic table. So this number right here is going to tell you the number of protons and the number of neutrons. So the number of electrons is the same as the number of protons. So how do we figure out the number of neutrons? Well, this is pretty easy. Protons equal 1. Electrons don't weigh anything, so protons get a weight of 1. Each proton gets a weight of 1. Well, there's 8 protons. We know that because this number tells us right here. There's 8 protons. 8 protons equals 1 weight each, so 8 times 1 equals 8. There are 8 weights from protons. Electrons don't weigh anything, so they don't get any weight. There are 8 of them. 8 times 0 is 0. So far we have 8. 8 plus 0 is 8. Well, how do we know how many neutrons there are? Well, we have a total number here that tells you the number of protons and neutrons plus the number of electrons found inside of here, the weight of all of that stuff. You have 8 protons, 0 electrons. Well, how do we know how many neutrons we have? 8 protons give us weight, 8 electrons give us 0 weight, and we have 16 here. So 16 minus 0 is 16, so 16 from the total, minus 0 weight from our electrons, minus 8 weight from our protons equals 8. So 8 plus 0 equals 16. So that's how you know how many neutrons you have inside of here. So we'll do this one as well. So 7 protons protons each equal 1 on the atomic mass number, the numbers of weight they get. So 7 times 1 is 7. There are 7 electrons as well. Electrons don't have any weight at all, so they are 0. 7 times 0 is 0. So far we just have 7. Well, our total down here is 14. This is the number of protons and neutrons found inside of the nucleus, plus the electrons, all of their weight added up. So 14 minus 0 is 14, and then 14 minus 7 is 7. 7 protons and 7 neutrons. Now, the easy way to say this is just what's 12 minus 16, since electrons don't have any weight. But the technical weight would be the technical way is to do the 0. Now, the easiest way is to just 12 minus 6 is 6. 6 protons, 6 neutrons. How many electrons are there? There are also 6. Now, you guys will see down here that this is not always an equal number, not always an even solid number. Some periodic tables round it up just for simplicity's sake, but that is not technically correct. Now, down here, all of these little tiny different digits. The vast, overwhelming majority of oxygen atoms on the planet have 8 protons, 8 electrons, and 8 neutrons. The vast, overwhelming 99.9 some odd percent of them all out there in the environment do. But every once in a while, some of them have different numbers of neutrons found inside of the nucleus. Now, you can't have a different number of protons. If you have a different number of protons, you are a different element. The proton number cannot change. The number of electrons can change, and the number of neutrons can change. The number of protons cannot. Anyway, we have 15.9994 here. So the vast overwhelming majority of oxygen has 8 neutrons inside of it. So 8 plus 8 equals 16. But some of them don't. Some of them have less than 8. Some of them have more than 8. A very, very, very small percentage of all the oxygen molecules out there are different, slightly different. Those different versions are called isotopes. They exist. Some of them are radioactive, which we'll talk about in a second, but they are just different versions of elements that exist in nature. They just have a different number of neutrons. Now, since they exist, we have to average them in to the atomic mass of that element as overall. The vast majority of them all have 16, so 100 million 16s averaged together with maybe 40 70s, 40 10s, 40 6s, the different numbers of neutrons that are out there, and that's what spits out the 15.9994. It's just enough difference out there to skew it from being a perfect 16. So for our purposes, you guys can just round it off, but just be aware that what this really does mean, these extra numbers here. So the atomic weight down here, the atomic mass, like I mentioned all again, is the average of all of those things that, all the different versions of this element that are out there, all the different versions of oxygen. So what is an isotope on a technical level? So I just kind of briefly mentioned this. So here's carbon over here. So carbon 12, the number 12. So carbon is number 6, the atom 6. 12 is its atomic weight. 6 protons is found on the periodic table. 6 neutrons is the normal state for carbon. Carbon 12. It has 6 protons, 6 neutrons. 6 plus 6 is 12. Gives you the carbon 12. The average normal version of carbon. Now, there are other versions of carbon out there that have more or less neutrons than they normally do. Carbon 13 has an extra neutron. Carbon 14 has 2 extra neutrons. They don't exist very often. They're very uncommon, but they do exist. So since they do exist, you have to average this together. You have 99 6s, 1 7, and 1 8. You got to average all that together, and it's going to skew it from being a perfect 6 to like 5.999997 or something like that. So just enough to skew the number. So that's what these are. So isotopes are different versions of the normal, most commonly occurring form of that atom out there. Sometimes isotopes are radioactive. When they're radioactive isotopes, not all isotopes are radioactive. They don't really like to have different numbers of neutrons inside of them. So the nucleus shakes and rattles and is not very stable. It shakes and wants to fall apart. So every once in a while, what will happen is on a very controlled basis. It happens over a very set period of time, kind of like a birthday kind of thing. It rolls around on a very controlled basis. One of these neutrons will break off. It'll shatter and break away from all the energy that's being contained inside the nucleus. It's just not stable. So that little shattering nucleus, that neutron being emitted, being sent away, is what in that form of energy and all that stuff is what causes radioactive poisoning, radioactive problems. So when those neutrons come in contact with you, they mess up your cells, they mess up your DNA. The energy that's also contained inside of this atom as it shakes and rattles and tries to fall apart is also going to cause problems. So as it releases neutrons, it will release one, and then it will get down to 6, and it won't be radioactive anymore. So they decay. That's the concept of radioactive decay, if you've ever heard that before. They're getting rid of the extra neutrons to try to get down to what they want to be, which is the normal state of carbon, or whatever the element itself is. So there's a couple of questions for you guys if you want to go over these. So let's talk about what happens when you add different atoms together chemically, when you join them together. So if you take more than one atom and you stick it together using a chemical bond, which we'll talk about briefly, you get something called a molecule. So a molecule can be one or more atom of the same thing, or one or more of the same atoms bonded together. So you can have a bunch of oxygens or a bunch of oxygen and hydrogen. That's a molecule. Anything that's got one or more atoms bonded together. They don't have to be the same, and they don't have to be different. Anything that's just got one or more atoms stuck together in it, joined by some sort of chemical force. So these are water molecules down here. Oxygen bonded to a hydrogen. This is one molecule here. You could have an oxygen bonded to an oxygen, and that would be also an oxygen molecule. But what you see here is an oxygen bonded to two hydrogens, a water molecule. Also, you have one molecule bonded to one molecule. That is something called a compound. Molecules of different elements bonded together. So if it's oxygen and oxygen, it's a molecule. It's the same. If you have oxygen and hydrogen bonded together by itself, that's a molecule. If you have oxygen and hydrogen bonded to more than one oxygen and hydrogen compound or molecule, that's a compound. So molecules can be oxygen, oxygen, oxygen and hydrogen. Compounds are oxygen and hydrogen plus another molecule of oxygen and hydrogen. So a water molecule, you get more than one water molecule together, you get the compound of water. So that's kind of how atoms are put together in the sense of organizing them together in molecules and compounds. So how do atoms form bonds? How do atoms stick to each other? Why do they stick to each other? Why do they need to stick to each other? And how do scientists classify the different ways that they stick to one another? So you guys are probably familiar again with this concept of an electron floating around the outside of that nucleus. So the nucleus is here. And our electrons are going to be floating around the outside of the nucleus on something called an energy shell. So electrons, for our purposes, they're going to have more than one energy shell. They have quite a few of them. But for our purposes, we're really only going to be concerned with the first two. There's quite a few more that go on the outside. So not just two energy rings that contain electrons, but more than that. There are more than that. But we're just going to be concerned with the first two. Anyway, so you have a nucleus and you have one little ring of energy that can contain electrons that swings around the nucleus. The very first set of rings can contain two electrons. That is how it's set. That is the most it can hold. It can hold less than two, but no more than two. The next ring of energy can hold up to 8. It can hold no more than 8 or less than 8, but no more. Now, atoms are happy when this outside electron shell, it's called a valence shell, is full. If you have just one valence shell, it can hold up to 2 electrons. If you have 1 electron, you are not happy. You want 2. So until you get 2, you're going to be a very unhappy atom. You are going to try to bond with someone else to try to get your second electron. You can either take it away from some other atom or you can share it with them, but you're going to try to bond to get that second atom from someone else. Now over here, this guy, carbon, has the first energy shell, and he already has more than two atoms, or he has two electrons inside of there. So he has more than two. So if you have more than two electrons, anything higher than helium, automatically has to go to the second energy level. If you have three electrons, you can't hold them in the first one. You have to go to the second energy level. Now, the second energy level can hold up to 8 electrons. The closer you are to 8, the happier you are, up until you get to 8. If you have 8 electrons, you will not bond with anybody at all. You are a happy atom. If you have 2 over here, you will not bond. You are a happy atom. Now, the closer you are to 8, the more you want to get to 8. The closer you are to 1, the more you just want to get rid of the one you have and just have 2. So that's kind of how this works. So the more available spaces for electrons out here, the more bonds you could form. Hydrogen can form 1 bond. He can only hold 2 electrons. Carbon can form 1, 2, 3, 4. He can hold up to 4 more electrons to have 8. Nitrogen can form 1, 2, 3 more bonds, whereas oxygen can only form 2. So once they get up to 8, they are happy, they are stable. They're either going to steal 2 more electrons from another atom or share electrons with another one. So the closer you are to 8 or the closer you are to 2, the happier you want, or the more you want to bond, up until you already have 8 or 2, and then you will not want to bond. You will be happy. So that's the word form of what I just talked about. So chemical bonds are the ways that atoms gain and share and lose electrons to get to that stable state of having 8 or 2, where they're not wanting to bond anymore, where they are happy, they've got the electrons that they like, they are going to be stable. So the concept of electronegativity determines how likely atoms are to bond with one another. So the electronegativity scale ranges from 0 all the way up to 4. So atoms that are really close to having almost 8 or almost 2, or having, so this oxygen molecule has a 7 on his outside shell here. He has almost up to 4. If you have 4, you're not going to want to bond. This guy's not going to want to bond a whole lot. He only needs 1 more electron. He doesn't really need to bond super much. This guy over here, our sodium atom, it's chlorine, sorry, sodium, he only has 1 outside electron floating around him. Oh my gosh, he's so ready to get rid of that one. He wants to get rid of it so bad. So his electronegativity number is going to be really, really, really low, down in the negative. So the closer you are to the 0, the more you want to get rid of the outside electrons. Whereas the closer you are to the 4, the more you just want to get 1. You don't really want to give away the 7 that you have. It's difficult to get rid of the 7 that you've got. You just want to get 1 from someone else. The closer you are to 4, the more you want to take 1 from someone. The closer you are to 0, the more you just want to give the one you have away. So this concept of electronegativity influences how atoms bond. Do I want to give one away, and are you willing to take it? Or do you want to give one away and I'm not willing to take it? So if I'm willing to give one and you're willing to take it, we'll bond together. Whereas if I'm wanting to give one away and you're wanting to give one away, we're not going to bond together, because that won't make either of us happy. So the farther you are in electronegativity numbers, the more likely you are to bond. So the really far apart atoms on the electronegativity scale that have drastic swings are more likely to form something called an ionic bond. And this is where one atom steals an electron from one another. So this atom of chlorine, as you guys can see, has 17 electrons in total and 7 floating around on his outside valence shell, 7 electrons. Now, is it easier to get rid of 7 electrons or just to gain 1? It's easier to gain 1 than it is to get rid of 7. 7's a lot of energy to get rid of. It's easier just to gain 1. Now over here, our sodium atom only has 1 electron floating around his outside valence shell. Now, on an energy scale, is it easier to gain 7 electrons or just get rid of 1? It's easier to get rid of 1. So this is how an ionic bond works. These guys are very, very, very drastically far apart on the electronegativity scale. So what's going to happen is these guys are going to link. They're going to form a bond where this electron right here on that outside valence shell is going to move to this outside valence shell. And when it does that, it's going to link those two atoms together permanently. So what's going to happen is this guy right here is going to give up this electron, which gives him, as you guys can see over here, 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons floating around on his outside shell. That's exactly what he wanted. This guy over here, our chlorine atom, now has 1, 2, 3, 4, 5, 6, 7, 8 electrons floating around his outside shell as well. That is exactly what he wanted. So by bonding, this guy had to give up 1 atom. That was our electron, excuse me. That was really easy. This guy got to gain 1 atom. That was really easy. I'll permanently keep yours. You can permanently give me yours. You'll permanently be happy, and I'll permanently be happy as long as we're bonded together. This is what forms salt, sodium chloride. Now, when this happens, this guy is supposed to have 11 protons, which he does inside of his nucleus. So if you remember, 11 protons needs 11 electrons to counteract that positive charge. Now there's just 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just 10 positives, or negatives, excuse me. 11 positives, 10 negatives gives us a +1 charge over here. Now over here, our chlorine now has 1 more electron than it does protons. 18 electrons, 17 protons. So now we have 17 positives, 18 negatives. Now we have a -1 charge over here on this side of this atom. Anyway, let's move on to the next type of bond called a covalent bond. Now, sometimes atoms that share a similar electronegativity number will form bonds as well. And this forms when atoms that can form bonds with multiple different atoms. So you can see here we have a carbon atom, and it has 1, 2, 3, 4 outside electrons. Now, the chances of you finding another carbon atom out there that have 4 other atoms that you can bond with to form C2 is decent. But it's a whole lot easier for you to find 4 hydrogen atoms and just stick to that. That's a whole lot easier. There's a lot more hydrogen than there are carbon, so just stick to all the different hydrogen atoms. Hydrogen's super, super, super unhappy. It has 1 electron. It wants to have 1 more just to get up to 2 to be happy on its outside shell. So it's really ready to bond with pretty much anything out there that will take it. This guy has 1 electron. That hydrogen's going to bond to him. Going to bond here, and the other hydrogen's going to bond to there. And now what happens is you end up with hydrogens that are sharing 1, 2, 3, 4 hydrogens that are sharing 1, 2, 3, 4 electrons with this carbon molecule, or carbon atom, excuse me. So the carbon atom has 1, 2, 3, 4 of his own electrons and 4 electrons that he's sharing with the other hydrogen atoms around him. So he had 4 from the hydrogen, that are 4 from himself to give him 8. He's happy. These guys had 1 from themselves, and now they're sharing 1 with the carbon atom, and now they have 2 each, so they're happy as well. So everybody shares, everybody gets what they want. These guys get 2, this guy gets 8, so everyone's happy. This is called a covalent bond. Co meaning together, valent meaning valence shells, so sharing of the valence shells. So water forms a covalent bond as well. This is what holds water molecules together. Now, holds the atoms of water together, the oxygen and the hydrogen bonds together. Well, anyway, so since this concept is kind of different, if you guys will flip back here, you guys will see here that these guys are spaced equally, sharing their space equally with this carbon atom. There are 4 electrons, 1, 2, 3, 4, which means there are 4 spaces for these hydrogens to equally disperse and spend their time equally rotating around the carbon atom itself. So there is no pull on one side or the other. They equally spend their time rotating around the carbon atom itself in the middle. Now over here, this is our water molecule. You guys will see here oxygen only has 2 electrons, 1, 2. It only needs 2 hydrogens to make itself happy. So the 2 hydrogens will bond to it, but now what's going to happen is there's not 2 more to balance it out. So you're going to have an unequal spin. You're going to have these guys are going around, which puts them over here, and then nothing over here. So extra positives are going to be on one side over here, positive, positive. So 2 positive charges are over here, and there's nothing over here. So this part of the molecule here, this water molecule, is going to become positively charged. It's got 3 positives over in one side over here, positive, positive, positive. 3 positive charges and 2 positive charges that don't have anything to cancel them out. So positive, positive. A slight positive charge will be over here on this electron, or on this molecule. Whereas up here, they're all dispersed around. There is no space where you have an equal positive. They're all equally dispersed around. Over here, what you will find on this guy is since the positives are over on this side, you will find a negative charge over here. Over here, there's no positives, there's no negatives. They're all equally dispersed. They spend equal time around. You don't find positives, you don't find negatives. They spin around in equal distances. There is no positive or negative force. Over here, in these types of bonds, these types of atoms and molecules here, you have positive forces and a negative force over here. More positive over here since the extra protons. Negative over here since there's not more positive over here since it's all on one side. Now, what that causes is something called polarity. So, we'll kind of skip over this. So, in atoms that are really close together on the electronegativity scale, hydrogen and carbon, they're very close together. They equal out. You guys see that they spend equal time spinning around. They don't really have a pull to one side or the other of that atom. This is called a non-polar covalent bond. There is no positive pole. There is no negative pole. It is a covalent bond because they are sharing their electrons. It just happens to be one of the non-polar variety. Positive, 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 positive. It's balanced out by all the equal negatives. There is no pole on this atom. It is a non-polar version of a covalent bond. Now you'll see over here our water molecule on the other hand. Oxygen is a significantly higher electronegatively charged atom than hydrogen is. And since this number exists, oxygen is more likely to pull the electrons to it than hydrogen is. Oxygen wants to bond more than hydrogen does. So oxygen's selfish. It's going to pull most of the electrons to it, hold them for the most time over here, kind of like a racetrack. If you guys can see over here, the atoms are going to, the electrons as they move around, they spend equal time on each space. Now over here, what you find is this. One, they move around, and then the oxygen gets the electrons for the vast majority of the time. So as the electrons move around, you'll have way more electrons over here than you do over here, which leaves positive, positive with no electrons, and a bunch of negatively charged electrons over here. So that causes a pole, a charge to be over here. A negative over here, as I mentioned earlier, and a positive over here from the protons. This guy has no net charge to him. This guy does, which causes him to be something called a polar covalent bond. You could stick a magnet to him, and the positive will stick to the negative will stick to the positive. Over here, you will find this guy lacks a charge, where there is no positive. If you stick a magnet to him, he'll just sit there and float around like he's just doing his thing. Now, this concept of polarity gives water some very interesting properties, and it also forms something called hydrogen bonds. Now, this is pretty much unique to that hydrogen-oxygen concept, polarity, and things like that. So, since we have positive, positive, and negatives on this one side, if you guys know anything at all about magnets, you know positives tend to stick to negatives. So, the positively charged hydrogen over here, you guys can see that, just kind of sticks like a magnet to the negatively charged oxygen next to it. Positive sticks to negative, they hold each other just like a magnet. There is no sharing of electrons here. No bodies crossing electrons, no bodies sharing valence electrons or anything like that. So this is not a true chemical bond. It's more of a force of electrons holding each other together, kind of like a magnet. There's no sharing. It's kind of just an electric force holding them together. So this was what allows water to have some very interesting properties, which is what we'll talk about in just a little while. The positive sticks to the negative, and it just holds the two molecules together just like a magnet. Some more questions for you guys if you want to go over them. So here's the different properties of water that are some very interesting things that are only found in water. These different properties of water allow life on Earth to exist as we know it. Without the the ability for water to do these particular things, life would be very different. The environments that we live in, the environments that organisms on the planet live in would be very different than they are today. So one of the very interesting properties of water is brought apart by that hydrogen bond concept, the tendency for positives to stick to negatives, and so on and so forth. So one of them is called cohesion. It's that tendency for water molecules to stick to one another. That positively charged hydrogen here sticks to that negatively charged oxygen like a magnet. Water sticks to itself. If you've ever dropped water droplets on a table before and you knock them around with a table with a toothpick or something, you know they bead up. They don't just splat and float around. They bead up. Water sticks to itself. You can knock the water droplets into each other, and they'll build up into a bigger water droplet. Water sticks to itself because of that positive-negative hydrogen bond charge. Now, water also has a tendency to form hydrogen bonds with other things that aren't water. Since it's not really sharing electrons, it doesn't matter what the valence shells of the things that it's touching are. It works like a magnet. You guys know magnets, as long as whatever it's touching is magnetic, it'll stick to it. Same with water. As long as whatever the water is touching has a positive charge, the water will stick to it. It will. You guys have probably seen this idea before, with the idea of water climbing up a glass. If you've ever looked into glass before, you've seen the water kind of forms a little U shape, or maybe a test tube or a graduated cylinder. You see the water forms kind of a U shape called a meniscus, where it's flat in the bottom, and towards the edges of the glass it forms kind of a U, where it dips up the side of the glass a little bit. So the edges of the glass, the water is slightly higher than the middle. So the water is forming a hydrogen bond with the glass itself and climbing up the wall of the glass and sticking to the glass. So since water sticks to itself, that concept of cohesion, it allows water to have something called surface tension. So since something sticks to itself, it forms a slight magnetic force. Now, you guys have probably seen really strong magnets that are very difficult to rip apart, and then some that you can just kind of shake and they fall apart. The water forms a very, very light magnetic force with one another. Very, very, very weak. Essentially the type of hydrogen bond, you can kind of shake it and it'll fall apart. It's very weak. Now, that concept of it allowing to stick to itself does give it, however, some property of stability. It is slightly stable. You guys know if you drop something on water, it smacks for a second. Water just doesn't suck it in like air. It is solid. It does have a slight surface to it. Now, if you are lighter than water, or if you can disperse your weight equally, like this little water strider bug here, you can push down less force than is required to break the little magnetic hydrogen bonds in between the water molecules, so you won't sink. You can essentially just walk across the surface of the water. Now, we can't do that. Our feet don't disperse our weight well enough across enough surface area to allow us to walk, but these guys do. They weigh so little, their feet are so big that the amount of surface area that their weight is dispersed over is not enough to break the magnetic bond, the hydrogen bonds of the water, allowing this little guy to walk across the surface of the water. It's kind of neat. Now, cohesion, water sticking to itself, also is what allows water to climb up the roots of plants. So water will be evaporated through the roots It pulls a vacuum up the plant essentially. As the water evaporates, it pulls up more water behind it. The water sticks to itself. It's pulled up behind the water. As the water pulls up below it or above it, it's pulled up by that force, which pulls up more water, which pulls up more water, which so on and so on pulls up more and more water. So as the water is evaporated through the leaves, it forms a vacuum kind of concept, which just sucks up more water from the roots from plants. And they have specialized structures inside of them that allow them to for the water to move freely between the roots and the rest of the plants here. But this is essentially how this works. If water didn't stick to itself, if water did not climb like this, it would not be able to do this. The water would not be able to be pulled up the surface inside of the plants. It would just pool at the bottom, and the plants would not be able to hydrate their roots or their leaves or the rest of the trunk or any of their fruits or anything at the top. So, one of the other characteristics of water that is essential for life that it dissolves things. Water is known as the universal solvent. It dissolves pretty much everything. Water really is good at dissolving things that are termed hydrophilic, things that like water. Now, this has to do with how their their structures or their sugar structures, their molecules are put together inside of the water molecules itself. But for the most part, it's really good at dissolving polar solutes, if you guys recall, polarity. Things that are nonpolar don't have a charge, things that are polar do. And ions, things like salt ions and chlorine ions and things like that, which is why you can get salt water and things like that. So water is known as the solvent, the thing that is doing the dissolving, the liquid itself, the things that will have stuff dissolved in it is known as the solvent. Water is the universal solvent. Pretty much everything will dissolve in water. Whatever you are pouring in that water, however, is known as the solute. The stuff that will dissolve in the water is the solute. So in this case, it is salt. The resulting solution of both the solvent, the water, and the solute, the salt, is known as the solution. The polarity of the particular things itself, of whatever you're trying to dissolve, determines how well it will dissolve in water. So, if you guys recall, water is slightly is polar. So what's going to happen is oxygen is positively charged. The hydrogens are positively charged. Chlorine has a slightly negative charge. Positive and negative for the chlorines. The the hydrogens are going to stick to the chlorines and break it apart, rip it apart from the mass molecule itself. It's going to be able to bond to it to strip it apart. The chlorine over here is also going to be ripped apart by the negatively charged oxygen part of the water molecules. So the positives can steal the negative part of the molecule that's being dissolved, and the negatives can steal the positive part. If you are a neutral ion or an atom, you don't have a charge, you're not a molecule, you have no way to be stripped apart, you're not going to dissolve. So this is why if you drop an element of gold, it's stable, it does not have bonds inside of it, it's not going to be dissolved in water. It cannot be dissolved. There is no way for the water to rip it apart. Gold is nonpolar. Polar substances dissolve in water. Anyway, so once again, the slight positive charge from the hydrogen steals the negatively charged chlorine molecules from the salt, and the slight positive charge from the oxygen negative charge from the oxygen steals the positively charged chlorines from the salt, and it just rips it apart piece by piece, slowly but surely. From the salt crystals itself, you pour it in the waters, and eventually what's going to happen is all the water molecules are going to have all the chlorine and sodium that they can take, and you can't dissolve any more inside of that water, and that's termed a saturated substance. So things that don't dissolve in water are nonpolar molecules. I just went over that with gold. If you are stable, you have nowhere to be ripped apart. You can't be ripped apart. You just can't. It also has to do with the way that the lipid molecules are put together. So, a couple of things that water is really, really, really good at is resisting changes in temperature. Water takes a lot of energy to change the temperature of it. If you guys have ever been outside or had a swimming pool, it can be really, really, really hot outside, but your swimming pool is still really cold. It takes a couple of days for your swimming pool to be able to absorb enough energy from the sun to be able to heat itself up. Whereas maybe your sidewalk gets hot in maybe 20 or 30 minutes of just being exposed to the sun. Water does not change temperature very well at all. And since it doesn't change temperature well, it allows organisms to maintain a very stable environment inside through the use of water. Um, it also helps regulate the environment and things like that. So since water takes a lot of energy to make it become warmer, if it's been cold for a really long time, water tends to soak up the cold. It doesn't change to become warm. So if you have a lot of water around you, like the ocean, that has a lot of cold temperature stored inside of it, as the winds blow across that cold air, it picks up cool temperature that cools the wind down. So this is why cities around the coast, like San Diego and places like that, tend to have a much cooler climate than places that are in the middle of the country, like deserts or here in the summer and places like that. It's also why if you put a big block of ice in front of your fan, that it cools you down quicker. Because the water or the ice is releasing cool, which the water will then blow across and then cool, or the air then blows across and is cooling down as it blows across. So one of the other unique properties that's found in water is that it gets less dense when it freezes, which is interesting. Most things, when they freeze, the bonds inside of them, when they get cold, become condensed. They get closer together. They tighten up. And when they tighten up, they get more dense than they were at room temperature when they weren't frozen. So if you stick a piece of gold at room temperature and you weigh it and you freeze it, it's going to be more dense on the inside. It's going to be thicker than it would be. No, it doesn't weigh more. It's just going to be thicker and more tightly compacted than it would be at room temperature. Whereas water, on the other hand, has the very interesting property of doing the opposite of that. When water freezes, it expands. It forms a very crystalline structure. You guys can see here these kind of random molecules and how they're put together become very organized. The charges line up, the positives line up to the negative, a very, very, very structured, organizing thing here, which is why snowflakes look the way they do, ice crystals look the way they do. Crystals by themselves, the definition of a crystal is an organized structure, which is why they're also called ice crystals, kind of in the name. A very, very, very highly organized structure. Well, when this structure is formed, it traps oxygen inside of these holes. Now, when this happens, ice, as it forms, traps the oxygen inside, which causes it to float. It becomes lighter than the water underneath it, the liquid version of water. And since this happens, it floats to the surface, and it allows the fish and other critters and things that are in the water below it to still live. They can still swim around, they can still get food and the oxygen that they need. Whereas if ice was heavier than water, it would form on the bottom first and push the fish up, 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 up. And then eventually you would be left with about this much water for all the fish and everything to be swimming around in. They would be pushed up too close to the sun. Predators could get to them and things like that. Ice forms at the surface and then forms down, not from the bottom up. It forms from the surface first and then grows down. So let's talk about how water deals with changing chemicals inside of cells, deals with changing atoms from one thing to another, and how those different reactions occur inside of the body. So one of the things that's really important to deal with different types of reactions and things is the pH scale. And the pH scale deals with how acidic or how basic an environment is, or how basic or acidic a substance is. Now, essentially what this is it stands for the power, P, of hydrogen. Essentially the amount of hydrogen atoms that are found in a substance. Now, this isn't a hydrogen atom, it's a hydrogen ion. A hydrogen proton, one single proton without an electron. H+, it's missing an electron, a hydrogen ion. It is a floating around proton that is ready to just bond to things in the environment. The more H pluses you have, the more acidic you are. So, lots and lots and lots, or excuse me, neutral is considered 7. Something that is considered neutral, we'll talk about in just a second, has an equal number of hydrogen ions as compared to something called an hydroxide ion, an OH ion, which I'll talk about in just a second. Acidic substances tend to have lots and lots and lots of hydrogen plus compounds in them. Now, basic low pH concentrations, on the other side, they tend to have more hydroxide ions, OH negative. The closer you are to neutral in the middle, the more equal these things become. In the middle, you have one H, one OH. Over here, you have one OH, two H's, three H's, one OH, four H. You guys get the idea. Now, over here, it's the opposite: one H, one OH. 1H, 2 OHs, 1H, 3 OH, 1H, 4 OH. The closer you get to this way, the more OHs there are when compared to H's. In the middle, they're equal. The farther you get up to this side towards the strong acid part, the more H's there are when compared to OHs. So, the more H's you have, the more likely you are to dissolve things. The more OH's you have, the more likely you are to dissolve things. What you're trying to do is strip away other ions, other atoms, to balance out these concerns here, to make these things go away, to make this H into something stable, to make this OH into something stable, usually water. The more acidic you are, the more likely you are to dissolve things, to bond that H plus or that OH minus. The more basic you are into something, usually water. You don't want to be acidic. You don't want all those ions. You're going to dissolve something to get rid of those H pluses, to get back down to a normal state that you want to be at. So, the last little bit of this lecture is going to cover what the differences of organic molecule types are, what is an organic molecule, and then some of the very important types of organic molecules that are found for life itself on Earth, and found in every different type of living organism on the planet. So first off, what is an organic molecule? Every cell on the planet is going to contain, every living cell I should say, is going to contain 4 different types of organic molecules. Now there are 4 major types, you guys are familiar with these, and every single cell is going to have all 4 of them. That is one of the characteristics that is definitive to life. You have these things inside of you. You can find organic molecules, one of the 4 categories, in non-living things, but you will not find all 4 of them together. You may find 1, you may find 2, but not all 4. All 4 is a characteristic of living organisms. So what is an organic molecule? So an organic molecule is something that contains carbon and hydrogen bonded together. And the key word there is that they are bonded together. And it is only going to contain those guys that are bonded together. You can have more things. You can have carbon, hydrogen, phosphorus over here. But phosphorus will be bonded to not carbon and hydrogen. Carbon and hydrogen will be always bonded together. You can have other molecules out there that have carbon and hydrogen in them. But if carbon is not bonded to hydrogen, it is not considered an organic molecule. Carbon and hydrogen have to be bonded together. That is the characteristic of an organic molecule. Carbon and hydrogen bonded together. The different combinations of carbons and hydrogens give us different names for different structures that are found within these different types of molecules, these different types of organic molecules. Now, the different setups of those carbons and hydrogens are going to define the different types of biological molecules, the different types of organic molecules here. So if you have this structure, you're going to be considered one type. If you have this structure, you're going to be considered the other, this one the other type, and this one another type. So depending on which type of structure you have, of how your carbon and hydrogens are put together, it depends on what type of organic molecule you're going to be. So these are the 4 main types here. We'll break them down and talk about how they're put together and what breaks up each individual one. So carbohydrates, proteins, and fats are the 3 main types that you guys are probably most familiar with of organic molecules. Carbohydrates are commonly known as sugars. We get most of these things from our diets. Carbohydrate sugars could be fruit sugars, sugars you get from sodas and candies and things like that, naturally occurring sugars like fruit sugars and things. Proteins are going to be coming from meats and nuts and um, fish and eggs and things like that, beans. Fats you're going to get from lots of vegetable oils and greases and butters, frying things you're going to get fats from. So let's talk about what these different types of organic molecules are, what they're put together, and kind of how they're put together and what makes them up. So the very first type of that we're going to talk about is how these things are put together and what they're joined together as, and kind of what these classifications are. So um, these different types of organic molecules are put together out of things called subunits. So it's kind of like a brick wall. If you imagine a brick wall as a fully formed wall, you look at it, you notice there are smaller bricks. So a brick wall, there are smaller bricks that make it up. Each one of those little individual bricks is called a subclass molecule in science. Now, we have a fully formed carbohydrate, our brick wall. You have smaller things that make up that carbohydrate. Those are the individual bricks. Those are called subclass molecules. So the whole brick wall is the carbohydrate. The individual wall are called subclass molecules, things that make up the carbohydrate. So let's talk about the subclass molecules for a second. The very smallest version of a subclass molecule that you can uniquely identify as a carbohydrate, as a protein, as a nucleic acid, whatever it happens to be as a lipid, is known as a monomer. You can pull out one version of this one little guy by itself. You could set that on a table, and a scientist could measure, run some tests on it, and go, that is a protein. That is a sugar. If you break this in half, it will not be identifiable as a sugar anymore. The smallest amount of a substance that can be identified as one of those 4 different types of organic molecules is called a monomer. Mono meaning one. If you take more than one of those monomers that are all the same and you stick them together, you get a polymer. It's multiple copies of the same thing over and over and over again. Sometimes it can be different, but the backbone is going to be the same. So you might have A1, A2, A3, A4, but it's all A's. 1, 2, 3, 4, 5 appear. All the A's are really what matters. As long as this part is the same, it's going to be a monomer or a polymer for the most part. So monomers, one little version. A polymer is more than one of the carbohydrate or protein or nucleic acid stuck together in a chain. So this is a little brief introduction on how these things are put together. You can stick together chains of monomers by pulling out water molecules. So you have OHs on one side. You're going to strip this out. You're going to bond together. The OH is going to be removed as a water molecule, and the monomers will stick together. This is something called a dehydration synthesis reaction. So dehydration, the removal of water. Removal, hydration, water, the removal of water. So the 2 monomers are spliced together and water is removed out. You can have a hydrolysis reaction where you break apart those polymers into their monomers. You break them back apart where you put the water back in. So hydrolysis, the adding of water, splitting of water is what that means. Water splitting. The water molecule is put back in. The OH takes over on one side and the H goes back over on the other, and you split that monomer back up or that polymer back up into its earlier monomers again. So let's talk about carbohydrates to start with. So the smallest version of a carbohydrate, a monomer of a carbohydrate, is called a monosaccharide. Saccharide means sugar, one sugar. Monosaccharide, one sugar. This is a monosaccharide here. Carbohydrates are very simple types of sugars, or polysaccharides and things like that. They all have 5 carbons in them. 1, 2, 3, 4, and there's another one there that's slightly hidden. 1, 2, 3, 4, 5. 5 carbons and an oxygen ring. One of the characteristics of our sugars. 5 carbons and an oxygen. 6 carbons and an oxygen. They always have equal numbers of carbons and oxygens. That's our characteristic of a sugar. Carbons and oxygens, carbons and hydrogens bonded together. Carbons and oxygens are equal in sugars. That's your characteristics here. 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 oxygens. That's the definition of a carbohydrate. So, yeah, I just went over this part real quick with you guys. Pretty easy on this one. So, you chain together a couple of monosaccharides, or single chains of sugars. These things tend to be used for short-term energy use. Ribose is going to be used to make DNA. Glucose and fructose are energy sources. The more carbons you have, the more energy that's stored inside of you. Our bodies and cells and things will rip these things apart to steal the carbons out to make ATP to fuel your cells. So you stick a couple of those monomers together to form a polymer, and the different types of arrangements that those polymers are joined together in, you get different things called polysaccharides. So one is called a monosaccharide, more than one's called a polysaccharide, multiple saccharides, multi-sugars. Some of them are cellulose, different versions of glucose and fructose run together. It's structural support. It's used for keeping plants upright and allowing them to bend in the wind without breaking and things like that. Another version is starch, which you guys are familiar with in the form of a potato, which is used for energy storage. You're going to store tons and tons and tons of sugars and things in here. These are all just little tiny sugar molecules over and over and over again. And then when the environment goes bad, the potato plant can break apart these long carbohydrate chains to get the sugars out to use them for energy if it needs to. Our bodies use a form of a polysaccharide called glycogen, which is used for our version of long-term energy in our things like our liver. So proteins. Proteins are another form of biological organic molecule. And these guys are way more varied in their structures and the way that they're put together and the things that they do than the other biological molecules before them. So, proteins can form structural support. Proteins form collagen that keeps your face from being droopy. It holds your muscles tight in place. It holds the skin to the muscles and things like that. It holds muscles to muscles. It holds internal organs to muscles, and lots of important things your proteins will use to hold things in place. Structural support. You also have proteins that are meant to move things. Your muscles are made of proteins. Those types of protein fibers are distinctly different than the ones that are meant for structural, and they do actual work. They move things, they pull things. They're designed to do physical movement. Then you have transport proteins, which are designed to move things across the cell. It's essentially just a hollow straw. Storage proteins, which are meant to just literally do what they say, store things away for long-term use in case you need it. And then you have proteins which are designed to do work, break things apart, build things up, move things from place to place. Proteins come in all different forms, all different structured, and they are very, very varied depending on their unique, individual specialized usage within the body or cells. Well, every single protein is put together of building blocks. They're subclass molecules called an amino acid. Every single amino acid on the planet looks pretty much like this. They all have an amino group. They all have a carboxyl group. This is a car. This is the four wheels. This is an engine. The R group over here is something called the variable group or the side chain and things like that. This is what's going to be different for each of the unique types of amino acid. This is like saying car with four wheels, car with an engine, minivan, Chevrolet, sports car. It's whatever's over here makes the car unique and not just a generic vehicle. So these two parts here make it an amino acid. Whatever's over here makes it a different type of amino acid than its other type of amino acid. Much like over here, you have the equal amounts of carbons, equal amounts of oxygens. That's what makes you a sugar, but you can have different numbers, and that's what makes you a different type of sugar. You have to have this for an amino acid, you have to have this for an amino acid, but you can have in a different R group. As long as you have these two, it's what makes you an amino acid. So it's kind of what I just went over there. Amino acids are put together in a very unique way. The way that they're put together is called the structure of a protein. They're put together in a unique way based on the charge of the amino acids as they are put together, assembled in the ribosomes. So A positive charge is going to be put together first. It's kind of like printing paper. You have to print the document in the correct order for it to make sense. If it was all printed and jumbled out of order, it wouldn't read correctly, and it wouldn't be the correct document that you want. So um, imagine like a giant long receipt paper. You print a positive sign first, you print a negative sign next, you print 3 positives, 4 negatives, 6 positive, 8 positives, 6 negatives, and they're all printed in a precise order, which is how this protein needs to be assembled. All of these amino acids that are going to be assembled in the ribosome have different charges. They are all put together one at a time, and the way that each one is assembled one after the other, positive, negative, negative, positive, is going to influence how the protein folds together, how the amino acid puts together, how the protein functions, how it's put together, and eventually if the protein works or not. It has to be put together and printed, if you like, in the right order, or it won't work. So you have the very first little bit of a structure of a protein is called the primary structure. And that's going to be a straight, just kind of positive, positive, negative, maybe 2 or 3 amino acids just kind of put together in a little line, just kind of getting ready to start getting a shape put to it so the protein will work. This is the most basic function of a structure of a protein. It does not work. It does not function. It does not do anything yet. So the next structure is called secondary structure. And this is what happens when there's enough of the protein chain added together, enough of the amino acids, that this positive charged amino acid up here can curl back and click to this negatively charged amino acid back here. It'll rotate on itself and bend to touch it. So there's 2 types of secondary structures. There's an alpha helix, which is one, imagine like a pasta noodle, just one twist. And then there's another form of folding called a beta pleated sheet. It looks kind of like the accordion dolls that you make in elementary school with the little legs. You use a plastic bag for the body and construction paper that you fold for the legs with the little heart feet. If you've ever made one of those, you know exactly what I'm talking about. It's just a little folded chain of amino acids. So once these structures start to form, they will be added onto more and more amino acids will be added to the growing amino acid chain as it's printed. These structures, this positively part of the charge structure up here, will start to fold back on the negative part of the structure over here. There's alpha helixes that don't print anything for a little while that makes a structure, and then it'll program a beta pleated sheet, and then another beta pleated sheet, then an alpha helix. It's just the different orders that they're printed in. So the beta pleated sheets will fold back on the alpha helix, and the alpha helixes will fold back on the other alpha helix. It depends on how they're put together and how they're printed. You guys can kind of see that down here. So as these guys are printed, they start to fold back on one another. They start to click on one another and form bonds with one another based on charges. That forms something called tertiary structure. Once the protein is completely done printing, it will be fully assembled and folded in the correct order. That is called tertiary structure. You can see here our alpha helixes and our beta pleated sheets. They're all connected together, folded back upon one another. That is tertiary structure. This is a fully functioning protein that does what it needs to do. It can be an enzyme, it can be a structural support protein, a muscle protein, anything that it's supposed to be. This protein will be able to do it. It has now been fully printed and fully assembled. Now, if you look down here, you'll see we have our light purple protein and a dark purple protein. If you have one fully assembled tertiary structure protein and you add it to another fully assembled tertiary structure, one or more protein, so it doesn't have to be just one, it can be more than one. So you have one protein plus at least one more, so 2 or more proteins stuck together that are both in tertiary structure, that both can work, you get something called quaternary structure. So one or more fully formed proteins that are joined together. Sometimes they join together because this protein can do half the job, this protein can do half the job. They join together to do the full job. Things like hemoglobin work like this. Maybe they work better together than they do separately. So they will form quaternary structures, groups of proteins put together. So another type of biological molecule is nucleic acids, and DNA and RNA are the 2 types of nucleic acids. They contain genetic information, which is the code for all life. It's coded for in things called nucleotides, which is the monomer of nucleic acids, the subclass molecule of a nucleic acid. A nucleotide is made up of three different things. You have a phosphate group over here. Phosphorus right there is what gives it its name. This is what makes a nucleotide a nucleotide. You have your sugar here. It's either going to be deoxyribose in DNA or ribose in RNA. And one of 5 nitrogenous bases. Now, this will not change. These two other things can change. If it's DNA, it will always have these two. If it's RNA, it will always have this one and ribose, not deoxyribose. So DNA will always have these two things. Ribose will have this one and ribose, not deoxyribose. But this one over here can change all the time. This one's not set between the DNA and RNA. This one can change. So DNA can have one of 4 different types of nucleotide of nitrogenous bases. There are 5 of them in total. DNA can have 4 of them, and RNA can have 4 of them. So DNA can have adenine, cytosine, guanine, and thymine. A, T, G, and C. RNA, on the other hand, can have A, G, C, and U. No thymine. DNA will never contain uracil, and RNA will never contain thymine. Adenine gets its name because it was discovered from the adrenal glands of cows. Not so sure about cytosine. Guanine was discovered from bat guano. Thymine, the thymus glands of cows, and uracil from urine. I'll have to look up cytosine where they discovered that one from. So, dehydration, synthesis, and hydrolysis, the exact same concept allows these different types of phosphate groups to bond to one another. So the phosphate group will bond to a carbon on the adjacent nucleotide, and this is what allows the nucleotides to bond together to form a DNA double helix or an RNA single helix to form our nucleic acids. So one of the other types is of organic molecules, is a lipid. Lipids are hydrophobic. They do not dissolve in water. They are nonpolar. They don't have a pole on them. The water molecules cannot get inside of this based on how the heads put together, the little head parts of this molecule. These guys, as you guys can see here, I mentioned earlier, the more carbons that you have, the more energy that you have inside of a molecule available for use. Now, you guys can see here, this is a lipid here. This is called a fatty acid. This is the glycerol head up here. The fatty acid tails down here have tons and tons and tons of carbon in them. This is why fats are really good for energy. Unfortunately, they have so much energy inside of them that your body doesn't often need this amount of energy, and it just stores them away for later use. This is too much energy for you to use. It takes a lot of energy to break all these fatty acids down, so your body would rather just not do it. It'll rather eat the sugar that you ate instead, so it just shoves the fats away for later storage. So there's 2 different types of fats. There's something called a saturated fat and an unsaturated fat. So I mentioned this is the little head region of the fat up here, and then our fatty acid tails. So the fatty acid tails, you guys can see, have tons of carbons and hydrogens bonded together. In a saturated fat, every single carbon has the maximum number of bonds that it could possibly form. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 3, and they can't form another one over here. There's the 4th one. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. All the carbons have 4 bonds. Everybody is maxed out. All of the bonds are saturated. Over here, you will see an unsaturated fat. This guy over here, 1, 2, 3, 4, he does not have the maximum number of bonds that he can have with hydrogens. He's got less hydrogens than he could normally have. These carbons formed a double bond with one another. He's missing 1, 2, 3, 4 total hydrogens. He's unsaturated. The number of bonds that he could have is maximized, but the number of hydrogens that he could have is not. He does not have the maximum number of molecules that he could have inside of him. So this causes a slight kink because of that double bonded carbon there. So when you eat a saturated fat or an unsaturated fat, or your cells do, this is easier to break down. it takes less energy. There's less bond, there's the same amount of bonds, but there's less atoms to deal with. It's easier to break this down. This is harder to break down. There's more energy that's required. So your body will break down unsaturated fats over saturated fats if given the choice between the two. Saturated fats stay solid at room temperature like butter. There's the you can see the very rigid controlled structure. It keeps them from not being able to move around on one another. Whereas unsaturated fats are often liquid at room temperature, things like oils. This slight kink inside of them allows them to have a non-solid but kind of a semi kind of runny texture to them. They're not solid, but they're not totally liquid like water. And this is what causes that slight kink. So, a couple more questions for you guys. And the little last experiment for you guys, you can run over this one if you'd like to in your book. But that's all that there is for this experiment, guys, for this lecture. If you have any questions over this lecture, please feel free to email me. If not, please have a good rest of the day. And please email me if you have any questions whatsoever.